To provide the context for this talk, I want to go back in time a little bit and talk about what's been happening in the recent past, or more precisely in the recent 50 years, because it is actually, this year is actually the 50th anniversary of the relational model for databases as it was presented by Edgar F. Codd in 1970. It's really changed the way we think about databases. Back in 1970, databases looked nothing like what they look like today. To be honest, I wasn't there. I don't know what they look like, but apparently the two major competitors, or the two prevalent architectures, were the hierarchical model and the network model. So Codd proposed this relational model, which is based on mathematics, on relational algebra and relational calculus. We could go back a few hundred years further to talk about that, but I'll skip that. But it's very interesting stuff. So really quickly, just some terminology. Basically, when Codd talks about a relation, he means a table. A relation is a set, an unordered set of tuples. A tuple is basically a record or a row, and you've got attributes. So columns are referred to as attributes, or attributes these days tend to be rendered as columns in tables. In Codd's model, both the rows and the columns did not have any inherent order in them, so everything was addressed by name, and that was very important to him, to have that sort of layer of abstraction. And we can only imagine what things were like before. You kind of have to imagine pointers between files and all that kind of stuff, which he didn't think was very usable. What's even more fascinating, and I'm sure a lot of you who've studied any database subject at university would recognize this or something similar, was that already back in 1970, Codd talked about normal form. So his model did actually allow for something like what we can see on the top right, where you've got like a nested structure of essentially tables within tables, or in his language, relations within relations, or an attribute of a relation being of a non-simple type, which is another relation. So the example here is you've got employees, and I apologize, it was 1970. He did choose man number as the primary key for his employees in this example. So the employee table had a name and a birth date, just those are simple types, but it also had a job history and a children column, each of which is basically a table in itself. So then we've got the job history, which is a child of the employee. It's got a job date as its primary key, a title, and the salary history, which again is another relation which has a salary date and salary. So you can see this sort of parent-child relationship. And even though this was explicitly allowed, he did point out that there are a lot of benefits to actually not doing this, that the simplicity of having a two-dimensional column homogeneous array was much easier to work with. So he proposed this process of normalization, where you would turn something like we see in figure 3a at the top into something like we see in figure 3b at the bottom, where there's no parent-child relationship as such, but you've got foreign keys pointing back to their parent record. This is pretty standard normalization, and it's been pretty much the model ever since. So nothing too surprising. In fact, many of you will say, well, my database can't even do the thing at the top. I always had to do it like at the bottom. And that's not necessarily a bad thing. Now, fast forward. So one thing to point out as well, Codd's model did not actually include SQL. He did say that you need some sort of database language, but SQL was only invented in 1974 by Chamberlain and Boyce. They initially called it SQL, S-E-Q-U-E-L, a structured English query language. Due to trademark issues, they changed the acronym later to SQL, standing for Structured Query Language. The first actual implementation of the relational model only came to market in 1976 by Honeywell. This one did not support SQL. IBM released shortly after what they called their System R, which they had been working on for a couple of years, to their first customer, Pratt & Whitney. I don't know if they ever had any other customers. Those systems were really big back then, so they were like, yes, we have a customer. The real first sort of mainstream commercial relational database with SQL support was Oracle version 2. Yes, the first version of Oracle was Oracle V2, because Larry Ellison did not believe people would buy a version 1 product. So that was 1979. And it wasn't long after, in 1981, that because of the real-world impact that the relational model that Cod had presented in 1970 had over that ensuing decade, that he was awarded the ACM Turing Award for his work in relational databases. So at this point, the relational model really wasn't theory anymore. It had become a real thing. Relational databases were actually a real thing. And so when he was presented the award, Ted Cod gave this lecture, and he recognized that basically relational databases almost had become synonymous with tabular databases. But he points out some important differences, and I think those differences are even today still very relevant, because you can probably think of some tabular databases that you wouldn't call relational. For example, Google Bigtable or HBase, or that sort of tabular database, because they don't really provide that sort of set-based processing, which Cod called relational processing, that you would expect from a relational database. And the other thing that he noticed, even though he's been a critic of SQL for pretty much his whole life, that SQL had really helped people with their productivity. So one feature that he pointed out that he thought was very good was that you could write these SQL queries interactively at your terminal and then basically copy and paste. I don't think he used the term copy and paste, but you could basically use the same query within your application program. So you no longer had to, I don't know what people had to do before, but apparently not that. So that was a huge productivity boost, according to him. All right, so in the second decade, so SQL only actually became an ANSI standard in '86. And in 1990, Cod released the second version of his relational model. So this time it wasn't just a short paper, it was actually a pretty thick book. You can get the PDF for free. It's quite interesting. So I'm not going to read out this whole thing, but one thing that he re-emphasizes there is that the only compound data type in his relational model is the relation itself. So he's saying anything else would just add complexity without adding power. And you'll see why this is important in a second, because this is actually not what happened moving forward. In 1996, so we'll go really fast now, Ralph Kimball, anyone who's worked with data warehouses probably knows dimensional modeling, or at least has heard of it, and star schemas with fact and dimension tables. So he actually promoted the idea of denormalizing your data model for analytics, because you didn't really have the same sort of reasons for keeping your data highly normalized. You didn't really worry that much with update anomalies and stuff like that. You could manage that differently. And he saw huge performance benefits because of reduced number of joins, but also usability benefits to denormalizing your data. But when he talked about denormalizing your data, he really just talked about maybe going from third normal form to second or first normal form. And if you don't know exactly what that means, it basically still means you've got flat two-dimensional tables. You've just got a little bit of repetition. For example, you might have some transitive dependencies, which would be split out in a transactional system. In 1999, the fourth SQL standard was released, and this is where it starts to get interesting. So we finally get to see some modern SQL features, including common table expressions, you know, the with statement, that That only became standard in 1999, but obviously these days it's, you can't imagine SQL without it, really. What was also introduced back in 1999 and hasn't taken off quite as quickly, I would say, but is what we are going to talk about today, is the ability to have structured user-defined types and non-scalar data types, along with the unnest keyword. So a standardized way of querying those nested structures in SQL was introduced in 1999. 2003, another version of SQL came out, introducing support for XML. If anyone remembers 2003, XML was super hot. JSON wasn't really a thing yet, but everyone was doing XML. People were talking about, should XHTML become the next thing, or should it be HTML5? That was probably a little bit later even. And people were doing XML schema, XSLT, SOAP, all the XML stuff. So obviously had to be supported in SQL. And another feature which is used on a daily basis in SQL now, window functions were introduced at the same time. We're almost done with the history. Sorry, 2006, Apache Hadoop was released. I don't want to say too much about Hadoop, but I guess that the promise was you can just sort of dump anything on your Hadoop cluster and then extract meaning from it later. And it turned out that one of the top use cases, if not the #1 use case, was dumping tabular data and querying it in a relational way using SQL on Hadoop, which wasn't really necessarily what it was initially designed for, which is why in 2010, Apache Hive came out. There were other tools like Impala, and now we have Presto and Spark SQL and lots of ways to basically do the same thing. And Google, so again, 10 years ago, Google released BigQuery, which kind of provides a similar service just as a service in a much, I would say, more user-friendly way. And they did support SQL from the very start, but it wasn't until 2016 when they actually introduced proper ANSI SQL standard support in BigQuery. So they still have this option to use what they call legacy SQL. That's going to be deprecated at some point, maybe next year or the year after. So the recommended way now is to use ANSI SQL. It's interesting though, the default for many client tools is still to use the legacy one. So you always have to say use legacy SQL false. Also, just kind of as an aside, in 2016, another ANSI SQL standard was released, which included JSON support. So why am I mentioning XML and JSON? Because they really were, they really just kind of different formats to achieve the same thing in the context of a database, which is having this structured hierarchical data in your database and have a way to query it. So even though you could argue it goes completely against what the original inventor of the relational model had intended, people have been doing it all the time. Even before XML, they would squeeze CSV or all sorts of weird strings in there that had some sort of meaning. Like values weren't always atomic. People always had reasons to do that, and having XML and JSON support actually just formalized that and made it easier. But remember, since 1999, the standard actually supported arrays and structs. Okay, so why should we care, basically? So first of all, why are we interested in BigQuery? BigQuery is Google Cloud's native data warehouse offering. I put data warehouse in quotation marks because it's not really the sort of same product as Teradata or any of those products, but it, and I wouldn't even say it's really like an RDBMS. It is intended for analytics, but it is increasingly looking like an RDBMS. There's a lot more support for DDL and all those kinds of things. But ultimately, what it is, it's kind of got two main features. It's got infinite column-oriented tabular storage, and you just pay for what you use. And then to access that data, it provides you with massively parallel serverless compute. And an API that you can send ANSI SQL queries to, and you get back a result if your query is valid. And one feature that maybe not too many people know about is its support for nested and repeated fields. So this is taken straight from a Google blog. So a nested field, if we can see the example at the top, we've got a transactions table with 2 columns, an order ID and an order time, just normal scalar columns, and a third column, which is actually a struct. So from the transaction table's point of view, there's 3 columns, but the third column has 3 fields within it. So you can you could think of it as a table with 5 columns, but it is really, there's a level of nesting. So you've got this sort of record within a record. Now you might wonder why, like, is it really such a big deal? There's a couple of different reasons for using it, but I would say the main benefit is actually when you combine it with the second feature that's on this slide, which is repeated fields. In other words, arrays. So in this example, your transactions table has an order ID, an order time, just like the one above. And it may still have a customer, but that's not visible here. It's got a product array. And while you could absolutely have arrays of integers and arrays of strings and so on, in this example, we've got an array of structs. So in this transaction, so a customer might order multiple products within one transaction, and this keeps it all together in one record. Whereas in this traditional, more normalized model, that would be in a separate table, and then you'd have a foreign key in the order details table, or whatever you want to call it, against each record pointing back to its parent record. There's also something that, again, Cord would probably not have liked. Arrays have an inherent order. So you can see on the right-hand side, every record has an offset, which you can access if you want to. You can ignore it if you want to as well. But there is an inherent order to the data within your array. It may be meaningful, it may not be meaningful. That's kind of up to how you choose to use that feature. But again, why? Like, why should we care about nested and repeated fields? Like, isn't this literally denormalizing to below first normal form? So literally, I would say it is, because this is exactly 50 years later, enabling us to do what Dr. Cord told us is probably something we should move away from through the process of normalization. But there are a couple of reasons why people may choose to do it, and whether you agree with those reasons or not, there's a good chance that you will encounter data structures like this, and you will need to know what to do with them. So one reason is performance. The documentation actually recommends that you should denormalize your dimension tables if they are larger than 10 gigabytes, unless you've got huge amounts of updates and deletes going on in those tables. They actually use the word denormalize, and they mean to denormalize it back to that level that Dr. Cord described back in 1970, where you've got a nested hierarchy within your table. So way further than what Kimball would have suggested. Like going backwards way further than what Kimball would have suggested. Usability, that's obviously very debatable, but you could make a strong argument that in some cases, at least, a table that's got everything contained within itself is a lot more self-documenting. Like the relationships are kind of obvious, that the joins have already been done for you. You don't need to go looking for, or are there any foreign key constraints, and work out what the relationships are, or make a guess based on the name. It's already there. It's more like if somebody shares a JSON or an XML document with you, you've got all that. Hopefully, you've got all that data in a sensible hierarchy, and this is sort of the tabular equivalent. And I think that's actually one of the many good use cases for BigQuery as a tool to publish and share your data. So it does make sense from that point of view. But on the other hand, queries against these structures do require more advanced SQL constructs, which I will show you in my demo. And yeah, finally, like I said before, people have been doing this all along. I mean, that's what the XML and JSON support was for. And even without that, people would just squeeze that data into strings and do all sorts of things that I don't think are any better. In fact, I prefer if they use these native strongly typed structures. And I'll just show you some examples where Google takes advantage of this themselves as well. So the first common real-world usage scenario, I'm sure some people on the call have seen this, is GA360 or whatever it's called these days. It's quite a complex schema. It's a huge table with lots of nesting and attributes. But if you ever worked with Google Analytics and you wanted to query that data, one option that you would have been presented with is to export it into BigQuery, and then you'll get a highly nested structure. You might be able to see on the slide. So you can see, for example, the hits field in this table is of type record, and the mode is repeated. So it is basically, that means it's an array of structs. And then the struct is quite large, and there's nesting, but we'll see that later. Slightly more simple example is billing extracts. So this is something that we use internally quite a lot. If you are a Google Cloud customer, you can get detailed information about what you're being billed for in a very itemized way. And when you have that data exported, so one way to get the data, the preferred way is to have it exported to a BigQuery dataset. And I've just selected a few columns, but like, for example, we can see the service column is actually a struct that consists of ID and description. Same with SKU, location, they are all structs. So it's usage, but the interesting one really is the labels attribute on the right-hand side, which is actually an array of structs, which each have a key and a value. So this is used for tagging your resources, so you can attribute your spend back to certain activities, for example. And another example, this is something I played with recently. AutoML tables is an AutoML, auto machine learning service in Google Cloud. When you train your model, you've got your training, your validation, and your test data set. And then once you've trained your model, you can actually run that model against your test data set and export the results to BigQuery. And you can see, like in this example, so we've got the input columns here. The first, you probably can't see my cursor, but you've got the input columns. Then you've got the actual thing that should have been predicted. And then in this case, because it was a binary classification, we've got the score for true and for false. So the first prediction is obviously wrong because the true has got a higher score than the false, even though it should have been false. But you can imagine if you had more than two classes, this would become bigger, like you would have more entries in your array for each row. So each row here is actually maps directly to an input row in your test data set, but then the scores for the possible outcomes are given back to you in an array. So I think that's quite handy. You can do lots of interesting things with that. All right, before we get into the demo, some important rules for structs and arrays. In BigQuery, a lot of these things will also apply in other systems, but specifically in BigQuery. So the rules for structs are basically a struct can have any number of columns. Actually, I don't know exactly. There's probably a limit somewhere, but you can have a lot of columns, and the columns can be of any type. So they can be like a simple type, they can be a struct, or they can be an array. You can have nested structs, and you can nest up to 15 levels deep. It is important to know that structs are not orderable. Obviously, there's an order within the struct, but you can't write a query and then order by your struct column. And you can't group by it or do a distinct or partition by. There's limited equality. So you could potentially use it in the where clause or do a join. It's a pairwise ordinal comparison, so it ignores the field names, and the data types have to be compatible. If that doesn't work for you, you can always manually compare individual fields in your structs. For example, if you wanted to do some sort of less than or greater than comparison, that's not supported out of the box because there's just no way that BigQuery would know how to order those structs. Arrays also have a lot of rules. Arrays are probably even more restrictive. So an array is an ordered list of 0 or more elements of any non-array type. So that means like you can have an array of integers or an array of structs of whatever, but you can't have an array of an array. If you wanted to have an array of an array, what you can do is you can have an array of a struct that has an array in it. So in this example, we have basically we want to have an array of arrays of integers, but we sort of have to squeeze the struct in between to make BigQuery happy and allow that. You cannot have null elements in your array so they certainly can't be persisted. They also can't be in your output result set when you write a query, but you may have them in your subqueries as long as that doesn't surface all the way to the top. If you have a null array, which is not the same as an array with null values, that basically gets turned into an empty array. So you can't really, in your tables, you can't really distinguish if an array column is null or empty. Arrays are not comparable, so you cannot compare an array to another array. They're not orderable, and you also can't group by, distinct partition by either. Okay, so now it's time for a demo, and I will use that GA360 dataset. So I'll just share my other tab. So this is BigQuery, and I'm using the demo dataset. So one great thing about BigQuery is you've got these public datasets. This BigQuery public data is it's a Google Cloud project that's publicly accessible, and it's got a number of datasets in it. And there's stuff on COVID, and there's weather data and finance data, a lot of blockchain stuff, a lot of like census data, lots of interesting stuff. But I will use the Google Analytics. It's sample data. It's based on a Google store that sells like Google merchandise. And this is a sharded table. Don't worry about that too much, but basically it means it is horizontally partitioned by date. This is the schema. So you may remember this from before. So you've got lots of fields. I'll scroll through it. You see it's very, very long. But you can also see that there's a lot of nesting. So every time you see a dot, that's actually, it's kind of like object orientation. It is a layer of nesting. So you can see the totals field in the table is actually of type record. And within that record, we have, so it's a struct, we've got lots of different integers. So all of these like visits, hits, etc., they are all part of that struct. Then the other one that's really important that people will almost always want to use is the hits record. So it says record, but it's actually, it also says repeated. So it's actually an array of structs. So this one's repeated. So this one will be a little bit more interesting to query. And we'll get into that too. So you can see like how many times a page was hit within a session, and like what pages were visited, what products were looked at, and so on. Now I will actually, so I'll just do a very, very quick thing. So if I click preview over here, this is what the data sort of looks like. So you've got, see, these row numbers are just row numbers in the results that they're not actually in the table itself. So all of this, even though this looks like, I don't know, 10 rows or something, for the first row, it's actually just one row. We can see that the visitor ID and all of the totals are just a single row, right? And then we've got all these blank rows below. So it's a bit misleading, but I guess that's what you have to do when you try to render data that's not two-dimensional on a two-dimensional screen. Now, if I scroll further, so this kind of indicates to us that there is something coming, right? I'll just keep scrolling and scrolling and scrolling. By the way, selecting star is not generally recommended in BigQuery, but that's a different story. So here we can see, so with the hits, so we can actually see that within that session, which is represented by a row, actually multiple products were looked at or purchased. I'm not actually sure, but it doesn't really matter for this exercise. So so you can see that we have this one-to-many relationship between sessions and products that were looked up in a session. Again, in a traditional database, that would have been a one-to-many relationship, which meant having two different tables. Here, it's actually one table. So you could say the grain of the table, if you think of this as a fact table, is the session, but then within that session, you sort of have multiple things that happened or multiple products that were of importance to that session, which is somewhat different to Kimball's model, where you've got maybe a sales fact and a product dimension. But yeah, this just gives you a general idea. So what do you need to do to actually query this data and turn it into something that's maybe a little bit more human-friendly? So for that, I could absolutely run my queries in here. In fact, I could click Query Table, and yeah, okay, it's fine. I could write a query. But I will actually use a different tool, and it's really just for a very simple reason, and you'll see it in a second. So this will basically, it can be a bit slow sometimes, but that doesn't matter. I'll switch to this, there it came back. I'll switch to a tool called SuperQuery, which is a tool that has been developed by a company that we've purchased earlier this year. This is SuperQuery. It's just a different web interface to query BigQuery and also other databases, but in this example, BigQuery. The main reason why I'm going to use this is because it's got tabs. So if anyone's ever worked with BigQuery before, I know Google is working on this, but yeah, it doesn't have tabs in this interface. So it's annoying if you want to work on multiple queries or you want to switch back and forth between queries. That's the reason why I'm using this tool. But it's going to be exactly the same queries that you could run in the standard interface, and the results will be rendered a little bit differently. But again, there's no material difference to the result. So same thing. So what I'll do here, I'll just select star from the same table that we looked at previously. I'm ordering by visit ID just to make sure that we get the same result each time we run this query. That's why I'm ordering by something. We can see it's the same thing. It's a lot of scrolling and a lot of blanks. Okay, so we obviously don't want that. But the other thing that we can see on the left-hand side, it's just a different way the schema of the table is rendered in this tool. So, oh yes, thanks Star for posting the link. So you can see this sort of hierarchical structure being rendered. I'm actually going to speak to the team because they don't. Yeah, I really will, because they don't really make it obvious what is an array and what isn't. But what you can certainly see is the totals here is a nested field. In this case, I know it's not an array, it's just a normal struct. So what I can do, I've prepared this query earlier. If I was just interested in the totals, there's two things I can do. So one thing is I can let me just resize this because you can't see the query. So I can actually treat totals as a column. So I'm just to have some sort of unique ID and just to demonstrate what you can do. I've selected some standard scalar columns: visit ID, visitor ID, channel grouping. They are just okay. Actually, let me run this query for you because the result set here is out of date. So they're just normal columns, and then totals is a struct. So in this case, though, in my query, I've treated totals as just as a column. So what will happen is we get back the entire struct for each row. Okay, so we can see in the results that we've got our visit ID, full visit ID, channel grouping, and then we've got these total visits. See how it says totals.visits, totals.hits? That's actually because what was returned was the entire struct and not just the individual fields from within that struct. But I can say, or maybe I'm only interested in, it's another thing that I will talk to the team about, but it's not a problem. So let's say if I wanted to just see visits and hits and maybe page views as well, because it looks like they don't have too many nulls in them. I can address these fields within the struct, similar to what you might know from object-oriented programming, or if you had an alias to another table. So when I run this query, so now these have just become normal columns. So there's no longer a struct. It is actually, it's just 3 columns. So the 3 normal columns and then the 3 columns that were extracted from the struct. Now, if I wanted to give them a different name, I could do that. Whatever. That's so the structs are pretty easy as long as they're not in an array. I'll just give you a few more examples. Okay, this is pretty much the example I did before. What if I liked having the data in a struct for whatever reason, but I didn't want to return the entire struct? So what I have to do then is create a new struct as part of my query, which is what we can see here. So I'll just highlight this section here. So we can just use the struct keyword. You can think of it as a constructor function if you want to. We pass it the values. We give the struct a name, and then the fields inside. We could rename those as well. And then what you can see again is we've got the same columns. Actually, what I've done here too is just to demonstrate. Oh, this is, sorry, I need to run this again. You can add other fields to it. So you can put whatever you want in there. But it's a struct. So you can see it is rendered as totals.visits, totals.hits, totals.pageviews. So we've actually combined these 3 columns back to a struct. And like I said before, you can add other derived columns. There's no constraints on only having data that's coming from a struct back in your new struct. So in this case, I'm dividing page views by hits, but you could grab another value from outside of the struct as well. It doesn't really matter. Okay, that's pretty much what you need to know about structs for now. Structs, as I said, are really easy. And now let's move on to arrays. And I do realize that we're running short on time. So first thing, similar to what you can do with structs, where you can just select the entire column as is, we can do that with arrays as well. So hits is an array. So if I just select hits in my query, this is what I get. I'll get my normal columns, and then I'll get hits. And again, you can see it's kind of ugly and maybe not so user-friendly to work with. Now, maybe I'm only really interested in like one field, like the page title or something like that. So unfortunately, this will not work. I can't just say I want hits.page. Obviously, that won't work. But I just wanted to point out the problem. It doesn't work because it is an array and the shape doesn't fit. So it says here, cannot access field page on a value with type array. So we'll fix that. We'll see that on the next page. But unfortunately, you can't, just like with the struct, say I want the subfield. It doesn't work if it's an array. What you can, there's lots of different things you can do. So one thing is, and again, you might remember doing similar things with XPath or JSON path or any of those query languages that you would use to query hierarchical structures, where sometimes you're like, okay with, oh, just give me the first one. You can do the same thing in BigQuery, so you can use this array notation. So you can say hits, square brackets, offset, round brackets, 0, and then you can either return that, or you could say dot page, and you could even say, which is what you can see down here, or you could say dot page title. So that'll just give us the first. So we'll still have the same number of rows as before. So we haven't done like a join that multiplies rows or anything like that. We can do that too, but we haven't. We've just said, okay, for every session, just give me the first hits page title, because page and title are not arrays, but hits is an array. So we're saying first element from the hits array, then give me the page title. And if we run that, that's what we get. Now, sometimes you do want all of the pages, and one thing you can do is you can do a, sorry, this is just another example where, like you can have products which are arrays in themselves and then product name, but I'll skip that because we're running out of time. So I'll skip that one too. Okay, so one way to actually get the entire list of pages returned in your result set without multiplying the rows. So in a traditional model, like with fact and dimension tables or any sort of one-to-many relationship, if you do a join between the tables, then all the values are duplicated. That would be bad in this example, because see these counts, like the visits and page views, the reason why those columns exist is so that you can easily sum them up. If we just did a join between sessions and pages, then those values, those visit counts, would also be repeated, and they would no longer be accurate. So the page views, so if we have 11 page views and multiply that by 11, obviously that's 11 times too many page views. So what you can do instead is, so you can actually join your table to an array within itself. So what we're doing here is a couple of things to note. So the unNest keyword effectively turns the hits array into a table, and then we can join on that. So we're joining the sessions, so each row in the sessions table, to the hits that were previously in an array. Now they will look to the query engine like a table. Now, what's interesting too is, see, we don't have a join condition. In fact, it doesn't matter. I could actually say cross join. I would get the same result, because the join condition is implicitly there. There's already a parent-child relationships, and that's what we're joining on. If we wanted to add other conditions, we could. So we're joining the parent to its child array, and then if we then, because we actually want to turn the entire set of pages into an array, we're using this array ag function. And remember, arrays have an inherent order. So if you care about the order, you need to specify what you want to order by. And then we group by all of the other columns. So that's one way to do it. So I'll just run this query, and then I'll show you some of the other options that you can do as well. So one thing you can do too is, if you actually want to, so in this case, I've ordered alphabetically, but if you wanted to preserve the order, you would need to extract the offset of each element within the array into a separate column in this fake table that gets returned by unNest. So you do that by saying with offset as, and then whatever you want to call it. And that allows me to do things like, so I can actually order by the offset, and this guarantees that my new array will order the pages in the same order as before. I could also actually create an array of structs where I explicitly show the offset. So I'll use this example up here, where we're actually still ordering by page title, but we're also including the page offset. So we can, even though we're changing the order, we also preserve the original order by including the offset in a struct. So I'll run that for you as well, so you can see what I'm doing there. Unfortunately, this looks a little bit, again, I will talk to the team. Nothing's wrong, but I hope maybe we can come up with a better way to render this. I'll just show you just the that example here with a struct. So we can actually see that we're now getting an array of structs where we've got the page title and the page offset. This is the original offset as the data was ordered in the source from 0 to 10 in this example, because we have 11 items. But this new array itself is actually sorted by name. And you can see from my other examples, you can do a distinct. So if you don't want duplicates, like the duplicate over here with offsets 4 and 5, so you could remove those with a distinct. You could order descending. You could do a limit. You could say only give me the top 5, and all that kind of stuff. It's really not that different from any sort of other aggregate functions. So not too different from sum, min, max, group by. Sum, min, max, and then you need to always group by the other columns. But I think there is a more elegant way, which is doing this. So you can do a subselect. So you can actually basically do a subquery within your select portion of your query, and wrap that in this array constructor, similar to the struct constructor that we saw before. We can have this array constructor to actually turn the results of a query, which in this case queries an array itself, back into an array. So the benefit of this is you don't have to do all this grouping. You can actually just add a column to your select statement that is an array. There's a slight difference to in this case, it doesn't matter because every session has a page, but every hit has a page. But this is more equivalent to doing an outer join, where even if your array was empty, you would just get an empty array. Whereas in the example before, those rows with missing or empty arrays would have actually been removed from the result set. I'll just show you one last example, and this is it's just nesting it. So we've got a nested array. So within hits we have products, and this is just to show that we can do multiple levels of multiple joins to flatten our hierarchy from as many levels as we want up to into a single array. So in this case, we're joining hits, which is an array, to products, which is a child, and then we extract the product name from it. So I'll just run that for you, but you can already see the result there. So we can't actually see hits or pages or anything like that. We've just got a single array for each session with all of the products. I made it distinct as well that came up in that session. So I think that's all we've got time for. There's certainly some more nuances. I did have a more complicated example, which I decided not to go with, but maybe we can have another talk sometime in the future where we can explore these issues further.